Dear friends, welcome to this new session. In this session, we are going to learn what is meant by queuing theory. Why we need queuing theory? A queue is formed when there is service is required. Okay. For example, when you go to a ration shop, or when you go to a doctor's room, or when you go to a supermarket or mall, whatever it is, when the crowd is more and the service providing people is less, then you can see a queue. So queuing theory, or people say it as waiting line theory, it is going to deal and it is going to analysis how the queues are there and what is the behavior of the queues and how we are going to find the solution to reduce the waiting time in the queue or manage the queue. So that is what this unit, very interesting. Okay, next we are going to learn what is meant by a queue. The number of customers who are waiting to be serviced, they are waiting for billing session, and it does not include the customer who is billing. Can you understand? So the number of customers who are waiting to be serviced, they are in the queue. A person who is getting serviced is not in the queue. A queuing system can be described by the following terms. Input, how many persons are coming, how many customers are coming inside to get service. Then the service mechanism, what is the service mechanism we are going to use to service the customers. Then the queuing service discipline, how many channels you are going to use to service the customers. Finally, behavior of the customer. We can see different kind of behaviors of customers one by one in the forthcoming data. Now let us see what is input or arrival pattern. It is measured by the mean of arrival rate of inter-arrival time. Usually you see throughout this process, we are going to take the arrival process is going to be Poisson. And then the inter-arrival time is going to follow exponential distribution. So we now mention lambda as the arrival rate of the customer. That is the first notation we are going to use. The next one, service mechanism or the service rate. Okay, we are going to say the service mechanism or service rate is going to be mu. It follows exponential distribution. Now it is very important, the servers may be finite or infinite. Sometimes we have multi-server queues. Okay, there are number of channels which are more than one. So now we denote the channels by C. Okay, if C is 1, it is single server. If C is 2, 3, 4, etc., it is multi-server. Next, queuing discipline. It is very important what discipline we follow. Okay, for example, now we are waiting in the queue. Okay, what will happen? The guy who's standing first, he have to be served first. The guy who come in the last, he have to serve at last. Okay, now let us see what are all the common disciplines. We are going to use in our unit first come first serve, or we say first in first out, FIFO. So this is what we are going to commonly use. There are some situations, what will happen? The guy who come last will be served first. For example, I'll tell you, there is a room, okay, with a screen. The chairs are arranged like this, okay, one by one. 100 chairs are there. Let us assume. Now the rule is there is the only one way to enter into this room. So the guy who comes first, he have to occupy the seat number 1. The guy who comes second, occupy the seat number 3, 4, etc., etc. The guy who come at last, he will occupy the last seat. Once the movie gets over, what will happen? This is the only exit to go out, no other go. So the person who sit at 100, he will go first. The person who sit 99, the seat he will go second. So now, can you understand? The guy who came last, he will be served first. He can able to go first out. So there are chances, what? Last in, first out. So, but according to our syllabus, we are going to deal only first in, first out. Next one, system capacity. Now, the system capacity is nothing but the number of customers who is in the system. It might be finite or it might be infinite. Suppose a barber is keeping a shop. There is a barber. He had a capacity of 4 people to sit. So in the queue, 4 people to wait for get service, and the barber is cutting the hair. One guy is sitting here. So the capacity of the system is 1 plus 4. Okay, this is the capacity of the system. And capacity of the queue is simply 4. But suppose you think that a barber is shaving or doing the cutting in the road. It happens long back. When we are kids, it happens. The barber will come to the village and will go and cut the hair. There is no shops. In this situation, it is not finite. The world is open. So what will happen? Now we think that the capacity is infinite. Anybody can wait in the queue and he can cut the hair. The next one is customer behavior. This is very, very important. The reaction of the customers might be different. It has different behavior because if the queue is very long, there are some customers they want to be serviced. They need, which is very important for them. Okay, they'll be waiting patiently, but not the all. There are some customers will get irritated. They're impatient. Their behavior is different. Let us see one by one. Now, let us consider a customer is coming inside. He saw the queue is very big. Okay. Now, what he is thinking, before entering into the queue, he had thousands of questions in his mind. He is a very impatient guy. He thinks that if I wait in the queue, whether I will get the service or not, and a lot of oscillations. So, before he join into the queue, he think that I don't want to join the queue. Okay, he just skip the queue and he move away. It is called as balked. Before he enter into the queue, he decide that he don't want to enter into the queue. He's just moving out. It's called as balking. The next one, reneging. These guys are little different. Initially they thought, okay, let us wait for some time. They will enter into the queue after 10 minutes or 15 minutes. After certain period of time, they lose their patience. After that, they will quit. Okay, but in the balking case, initially he decide before he join into the queue, he is quitting. In reneging, he come into the queue and he wait for some time for the service. He loses its patience and he is moving. The next one is jockeying. Now you understand or you guess what it is. This jockeying can happen when there should be more than one queue. You should have 2 or 3 parallel queues. We used to see usually in the railway stations. When we go, 3-4 queues are there, what will happen? Some queue is moving very fast. In my queue, maybe 10 or 12 members are there in front of me. In the other queue, 20 people are there, but they will move in 2-3 minutes. Yet my queue is very slow. What I will do now? From queue 1, I will try to skip and jump into the other queue which is moving fast. Can you understand? A customer may switch from one queue to other queue due to the reason that it is moving fast or something else. Then it is called as jockeying. Next, the thing is we have to learn what is meant by transient state and steady state. So if the characteristics of the queuing system is dependent of time, then it says transient state. When it is not depending on the time, it is independent of time, then we say it as steady state. Okay, the symbolic representation is given. Let us see one by one. So, E is giving like this. A bar B, C, D and E. Okay, you can see at least one MCQ over this. Let us learn one by one. So, whenever there is a queuing model, first we have to speak about the customers. So, A is the probability distribution of the inter-arrival time. It denotes the arrival rate of the customer. Then obviously B is going to be what? Service time for the customer, service rate. And C already we said, C is the channels, number of servers in the system or the channels. And D, it is going to be the system capacity, right? maximum number of customers which are going to be allowed into the system. Either it might be infinite or it is going to be finite. And finally, E is going to be the queuing discipline, FIFO, FCFS, first come, first served, first in, first out, first in, last out. We have to check all these things. So this is the standard notation given by Kindle. We are going to follow this notation. And now, throughout our unit, what we are going to assume, the queue is going to have a Poisson arrival rate. Okay, A is going to be always M. Okay, it is denoted by M. The arrival rate is Poisson and the service rate is exponential. Inter-arrival time, all those things we say. So now, this is what going to change here. If we have a single server, I am going to put 1. If we have more than one server, if it is a multi-server, I am going to put K, where K may be more than 1. Next one, system capacity. Here also, as I said, my capacity may be finite or it might be infinite. And finally, the queuing discipline, what we are going to fix throughout our problem, all the three models of FIFO, first in and first out. In our exam problems, M/M/ is fixed. Similarly, FIFO is fixed. We have to understand the question, read the question, and we have to find whether it is going to be finite or it is going to be infinity, whether it is going to be a single server or it is going to be a multi-server. Okay, the next one is the basic notations. Whenever there is a queue, the number of customers will be N. I am going to use N as the number of customers. Sn. It is going to be the state in which N customers are in the system. Pn. Pn is going to have steady state probability. The number of customers in the system, if it is N, I will say it as Pn. Then P0 is very obvious. Okay, there is no customer in the system. The system is idle. Okay, if I have N customers, I will say Pn at steady state. If the probability having 0 customers or idle system, I will say it as P0. And now the arrival rate, as we said earlier, it follows Poisson distribution. So the mean is going to be lambda and the service rate is going to be mu. And very, very important here in the problem, we should be careful. If mean arrival rate is given, it is called as lambda. If the mean service rate is given, we have to take it as mu. Instead of mean arrival rate, if they say the mean arrival time, inter-arrival time, if they say 20 minutes, this is time, it is not rate. Rate means, I'll tell an example, every hour 3 customers will come. So the arrival rate of the customer is 3 per hour. This is your rate. But when I say the inter-arrival time is 20 minutes, then this is not rate. So what we have to see, you have to open your eyes. If the inter-arrival time is given, I have to take this as 1 by lambda. So 1 by lambda is equal to 20 minutes. Lambda is equal to 1 by 20 per minute. Now if I convert this into hour, lambda is going to be 60 into 1 by 20 per hour. So lambda is equal to 3 per hour. So you should be very, very careful whether the arrival rate is given or inter-arrival time is given. Okay, if the word rate is mentioned, so I will directly take lambda is equal to 3 per hour or 4 per hour, whatever it is. If they mention like this 20 minutes, 30 minutes, something like this, then what you have to do? You have to take this as 1 by lambda and you have to convert into lambda. And the same procedure happens for mean service time also. If mean service rate is given 4 per hour, I can take directly. If they say mean service time is 15 minutes, okay, in this case, what I have to take? 1 by mu is equal to 15 minutes. Mu is equal to 1 by 15 per minute. then I have to convert this into mu is equal to 4 per hour. Hope you understand. Next, it is very important what is rho. Rho is lambda by mu. People say it as utilization factor or traffic intensity or busy system. Okay, so it is very important. 3 customers are coming per hour, 4 customers are service per hour. So my traffic intensity or utilization factor or busy system is 3 by 4. That means now I want to find the ideal system. The ideal system is very simple. Since the total probability is 1, probability of busy system and probability of ideal system is going to be always 1. So probability of ideal system means we know the notation P naught. It is simply 1 minus rho. That's what we have to think. Is it clear? So next we are going to see one by one. Whenever there is a system, always there is number of person who was getting service, number of person who was waiting time in the queue, waiting time in the system, etc. etc. One by one let us learn. LS. What is LS? Expected number of customers in the system. What is a system? I said in the example, if there is a barber, he had 3 seats. In 3 seats, 3 persons are sitting, and 1 person might be sitting here, and he was serviced by the barber. Okay. Now, what is the expected number of system? This is the system. In the system, 3 persons are in the queue and 1 person is getting serviced. So the system is 3 plus 1, 4. This is an example. The next one is LQ, expected number of customers in the queue alone. So we are going to calculate number of persons in the queue. Okay. So we are going to bother only about how many people are waiting in the queue. Just only the waiting person. It is LQ. Similarly, WS, the presence, expected waiting time in the system. That means how much time the customer is wait in the queue and how much time it take to service. For example, it might be any service, billing service, cutting the hair, etc. etc. And similarly, WQ is going to be what? Expected waiting time of a customer in the queue alone, not in the... Now, the classification of the queuing models, probabilistic or stochastic model. When there is an uncertainty is happening, we don't know, like both in the arrival rate as well as the service rate. Then we say it as a probabilistic model because of the uncertainty. When the both arrival rate and service rate are constant or it is fixed, or we know earlier it is exact, then we say it as a deterministic model. There are some cases, what will happen? Mixed model. We know how many service providers are there in my company. For example, I have only 3 service providers. So what will happen? The arrival rate might be what? As some uncertainty. Suddenly 100 customers will come. Suddenly 1 customer will come. There is an uncertainty. Vice versa. Okay. The customer arrival may be fixed. The service rate may be changed. It depends on the service provider. So it is called as mixed model. Can you understand? Either the arrival rate or the service rate is not exactly known, then it is known as a mixed model. The next one is Little's formula. So this Little's formula is only for MCQ purpose, because for solving the problem I am going to use a different technique. Okay, different formula. So let us learn the Little's formula. LS, how to find LS? It is simply lambda into WS. Then LQ is lambda into WQ. The third one is WS. WS is going to be WQ plus 1 by mu. And finally, LS is going to be LQ plus lambda by mu. So this is called as Little's formula. But we are not going to use this Little's formula for problem solving purpose. Let us see how to consider the formulae what we are going to use, because I want to involve just only lambda and mu, whatever it is. So the easiest one I'm going to start is what? WS, waiting time in the system. It is going to be 1 divided by mu minus lambda. It is very simple. Then since I write waiting time in the system, expected number of persons in the system I can write now. So the formula is going to be mu minus lambda in the denominator. Just one lambda I am going to multiply in the numerator. So WS, LS. If you know WS, if you multiply lambda, you'll get LS. It's over now. The next one is similarly WQ. What is the formula for WQ? It is going to be mu minus lambda. I'm going to take this lambda again. Now if you multiply by mu, you are going to get WQ. And finally, now you have guessed what is LQ. Now you take this formula lambda, mu minus lambda. When you multiply with lambda again, it is going to be LQ. So if you remember WS, multiplication of lambda will give you LS. Multiplication of lambda by mu will give you WQ. And from WQ, if you multiply one lambda, you will be getting lambda square. Hope you understand. So this is very easy for us to remember. It starts from WS. When it's multiplied with lambda, LS. When it's multiplied with lambda by mu, WQ. When WQ is multiplied with lambda, it is going to be LQ. Okay. So we are going to use this formula for our problem solving purposes. So now we learn different models. So this is the case for M/M/1 infinite capacity FIFO. This is the formulas. Similarly, in the forthcoming sessions, I will tell the formula for the other models. So we are going to use 3 models in this problem. What are all the 3 models? M/M/1 infinity FIFO. M/M/1 finite. So K is some finite FIFO. And then finally, we are going to use M/M/K. It is going to be a multi-server. And here also FIFO is fixed. Here we are going to deal with what? Finite or infinite capacity. So these are all the 3 models we are going to solve for the semester examination, which is available in the syllabus. So for this first model, we have learned the formula. This formula is not common for all the 3 models. This is true only for single server infinite capacity model. Okay, so first one by one we'll solve the problem. In the next session, we are going to see the problem on infinite capacity single server model. Then and there I will give the formula for the other models to solve the problems. Thanks for watching, and we'll meet in the next video. Thank you guys.